Hello and welcome to the final presentation for our machine learning project. As everyone knows, COVID-19 has had a tremendous impact on our world. We hope that our project can help with COVID diagnosis and improve the accuracy and efficiency of COVID diagnosis by medical professionals. One of the models we trained was a convolutional neural network that was trained using chest X-ray data from three distinct classes: individuals suffering from COVID-19, individuals suffering from non-COVID-19 respiratory infections, and finally, healthy individuals. Next.
We found a dataset that listed various categorical COVID symptoms and the result of COVID diagnosis. This dataset was first cleaned. We replaced string values with integers, and then we imputed any missing data values by using k-nearest neighbors. The value of a missing data point was replaced by the most common value of the 5 nearest neighbors. Next.
And here's how the data looks like. Next.
The convolutional neural network was made from several convolutional blocks. These blocks contained a convolutional layer, followed by a pooling layer, followed by a ReLU nonlinearity. The most important hyperparameter that we chose for this network was the loss function. We implemented two loss functions, the first being cross-entropy loss, and the second being class balance focal loss. This loss function enables more efficient network training across unbalanced classes. Next.
Before we run the PCA, we standardize the data. After we standardize data, we use the data to run PCA and reduce the feature size from 8 to 6 while keeping the 0.85 variance retained. And after that, we run the logistic regression on that and get the results. Next.
In addition to running PCA on our dataset, we also experimented with feature selection utilizing ridge and lasso regression. We used a min-max scaler to make the data more easily processed, split our data, and applied lasso regression for feature selection. We then tested the accuracy of our data using a random forest classifier. After we repeated the process using ridge regression for feature selection. Next.
We implemented an SVM and scikit-learn to predict COVID diagnosis based on categorical symptom data. Prior to training the SVM, we first reduced the dataset by undersampling the majority class. This was done to A, address the class imbalance, and B, reduce fitting time. Next, we tuned hyperparameters using tenfold cross-validation. Hyperparameters tuned include the ratio of negative test cases to positive test cases of undersampling data, regularization, gamma, and the kernel. Lastly, we attempted to improve the performance of the model by using ensemble methods of bagging and boosting.
We would take k-nearest neighbor model to classify the positive COVID-19 cases with two features, context status with others and symptom score. The symptom score was created by summing 5 symptoms features. Also, the number of nearest neighbors used to train the model was optimized using tenfold cross-validation. The cross-validation scores were evaluated from the models with K's from 11 to 50, and the optimal value of K was chosen from the model with least error value. Next.
The figure you currently see is the loss and accuracy curves belonging to our first SIN model. As you can see, accuracy improved throughout training, with a highest validation accuracy of about 76% and a highest training accuracy of about 97%. Our final convolutional neural network model achieved the loss and accuracy curves you are seeing now. The highest validation accuracy was about 84%, and the highest training accuracy was once again 97%. These models were trained on the larger data set with class balance focal loss, which we believe accounts for the improvement. Next.
After we run the logistic regression and we compare the result with PCA and without PCA, we can see both the score are near around 0.95. The only difference is the running time of PCA is faster than without PCA. Next.
Results after applying feature selection using ridge and lasso regression were fairly high. The accuracy rating was very high for both methods at about 95 or 96%. However, the F1, precision, and recall scores were significantly lower than our accuracy scores. Next.
The first figure here shows the performance of the SVM as a function of the undersampling parameter. At an undersampling ratio of 4, that is 4 negative cases for each positive case, the performance of the SVM converges to a moderate F1 score of about 67% and an accuracy score of 95%. The next two figures show the results of the regularization and gamma hyperparameter validation, and we see that these two parameters have little to no effect on the overall model. Lastly, we tested different kernels, with the radial basis function kernel giving us the highest F1 inaccuracy scores, the polynomial kernel of order 3 being a close second. Next.
After training KN models with different Ks, the accuracy was generally high, but other scores were not as high. The precision increased when K increased, so I went and performed the optimization of K. After the cross-validation scores were computed, the mean square errors for different Ks were calculated. As the graph shows, when K equals 43, the MSE was minimized and the optimal value of K was 43. After the model was trained with 43 neighbors, and the result was as follows, which was generally higher than the model trained with lower Ks. Therefore, it can be said that optimization improved the KNN's performance. Next.
When reviewing the results from our first CNN model, we knew that we had two primary limiting factors. The first being our lack of access to data, and the second being that our data set was very unbalanced. We remedied the first issue by combining our data set with a pneumonia data set, which was much larger. And this actually led to an even greater class imbalance, which we remedied by applying class balance focal loss as our loss function. These two methods in combination resulted in an approximate 8% increase to our model's validation accuracy. Next.
The performance of logistic regression with PCA is pretty good. Accuracy, F1 score, precision score, and report score all around 0.95. And there is no further improvement on the model, but we discussed this may be a good model to choose to fit our problem. Next.
Our accuracy scores were high after applying feature selection for both ridge and lasso regression. Our F1 precision and recall scores were low compared to our scores for logistic regression with PCA. This may be due to the fact that lasso regression did not rule out any features, and ridge regression targeted features that did not vary significantly.
The performance of our SVM is mediocre. While the accuracy is relatively high, the precision and recall scores are significantly lower due to the unbalanced nature of the dataset. Further steps to improve the SVM performance were unsuccessful. Ensemble learning, in addition to hyperparameter tuning of gamma regularization, were unable to increase the performance parameters. We conclude this is due to the fact that, due to the small domain of each feature, the data is inherently inseparable by a hyperplane or hypersurface. Indeed, when examining the dataset, there are many data planes which share the exact same attributes and yet have different class labels. Therefore, we say that a hard classifier is unsuitable and a soft classifier with logistic regression would be better.
Performance of a KN model was not statistically significant compared to other classification models, so it is reasonable to conclude that other models could perform better in the prediction of COVID-19 cases than the KN model.
This concludes our machine learning final presentation. Thank you for your time.